Hello, welcome to Picture Me Coding with Eric Aker and Mike Mull. Good morning, my friend Mike. How you doing?
I'm doing okay. My particular neighborhood in Southern California has not yet burst into flame, so I got that going for me.
Oh, yeah, there's a lot of flames north of us, San Diego, where we are at, not having a lot of fire, but I hope they're doing all right up in LA. There's a lot of fire up there. It looks pretty scary, pretty devastating.
Yeah, one of my kids lives in Westwood, so we've been keeping a pretty close eye on it just to see if they're going to have to flee the city.
Yeah, it's surprising. The urban fires up there, I always associate it with more of the chaparral-y valleys without a lot of like urban jungle, but this is pretty gnarly. And those crazy winds, we had really, really high winds all week. It was weird,
Yeah,
the eerie weather.
reminds me of Joan Didion's piece on the Santa Anas.
I thought of that too. Well, if you're listening to us you're from Los Angeles or you have family in Los Angeles, we hope you take care. We will be thinking about you here. Just to mention it, if you would like to get in touch with us, we have an email address. The email address is podcast@picturemecoding.com. You can also reach out to us at our website, www.picturemecoding.com. And we have a Blue Sky account, and you can reach us there as well. Blue Sky also, Picture Me Coding. And Mike, this week I started a Patreon. Now, I was a little hesitant to do this, but this show's a lot of fun to make. I don't think we're trying to get rich and famous off of it, but it's a lot of work to edit it. And so I kind of thought, man, if we got a little bit of support making this show, we could probably hire an editor, a professional editor, someone who knows what they're doing. So we have a Patreon, and we could use your support, listeners. We have one Patreon level, because I'm new to Patreon. I didn't even really know it's not for like one-time donations. It's like these subscriptions. And our subscription level right now is a $4 a month subscription. You can sponsor our show. If you do so, we will read your name aloud. Thank you for your support. And your contributions will go to producing the show. So I don't know if anybody will sponsor the show, but if they do, we can use that sponsorship money eventually to hire an editor. What do you think, Mike? $4 a month?
Sounds like a good investment to me. But I was under the impression we were trying to get rich and famous. So I guess I have to confess that. So
If you were listening to two random guys talking about software and weird computer science things, do you think you'd be likely to be like, yeah, I'll give these guys $4 a month so they can get a professional editor to edit their show?
it probably wouldn't be the first thing to occur to me, but there's like podcasts where some guy talks for 6 hours about the history of Sparta or something like that. So,
Yes. Yes, that's true. Yes. People love those podcasts. I tried to give it a chance once, and I guess I just don't have the 6 hour podcast attention span. I'm like a 1 hour or less podcast attention span. Mike, this week I've been listening to a Billy Woods album. Remember our friend Randy? He talked about Billy Woods.
I remember him well.
Yeah. And so I was like, I got to try to check this guy Billy Woods out. So I listened to a number of his records, and there's this one weird one with this guy Kenny Siegel, who's a producer. It's called Hiding Places, and it's the one out of the ones that Randy talked about. It's the one that really stuck to me. They're all weird records, but none of them really grabbed me the way this one did. The first song on the album is called SpongeBob, and in my head, I just keep thinking of it as, oh yeah, the SpongeBob album. Let me go listen to the SpongeBob album. It's called SpongeBob. And you read the lyrics for this song, and it is going places. It's a weird song. It's a weird album, but I get it stuck in my head. There's something about the music and the lyrics together that they just kind of get in my brain. In this SpongeBob song, he talks about these war-torn places. It seems like the song might be like about surviving war, and maybe SpongeBob, he's like hard to crush. He can like reshape himself. I think that's kind of what's going on. There's like this weird stream of consciousness. I don't know how to parse it, but it feels very dense and interconnected. So I'm just going to read to you some of the lyrics from the song SpongeBob off the record Hiding Places. He raps, "Get fished out the hole like Saddam. Tough guys won't go alive, get found unarmed. An object in motion stays in motion. I wait till the sea calms, slaves like hammer, brawn, ships was yea long. It's too late for qualms with the hammer in the palm. There's something Shakespearean and odd about this language, and it's a weird record, but I really like it actually. Shout out to Randy for recommending Billy Woods in the first place.
Yeah, I've listened through a bunch of these too, a bunch of his albums as well. I find them challenging, but this one's probably my favorite as well.
Oh, you checked this one out. I really like this record. I felt a little bad I didn't love any of the other ones.
I think they are not the sort of thing you get on the first listen. They're not like stuff that you play in the club, but yeah, they're interesting enough to bear repeated listenings.
What you got?
Mine this week is an album that came out in mid-December from Jeff Parker and in collaboration with the ETA Quartet. It's called The Way Out of Easy. Parker is this guitarist who does collaborations with all sorts of people. He's very critically acclaimed. He did this one album in 2020. I think it's called Suite for Max Brown or something like that, which shows up on like a lot of best of the decade lists and stuff like that. But it's always been just kind of a wee bit too maybe avant-garde for me.
Really? For jazz guitar? I like jazz guitar. I usually feel like, hey, I'm grooving. This is cool. I like it.
Yeah, it's interesting stuff, but some of it has been, I don't know, just maybe a little bit too abstract for my taste. This one is just really beautiful. I listened to it over and over again, and it's only 4 tracks, all of which are kind of long. So it's 4 tracks that are all around 20 minutes, and they have kind of diverse styles. So they're like the opening track is called Funkadelic, and it definitely lives up to its name. And then the second track, which is probably my favorite, is called Late Autumn, and it's got this sort of melancholy, minimalist feel to it. Very moody, and I don't know, just been exactly what I needed of late. So
Moody sounds good. Moody jazz guitar.
yeah, that'd be a good review for it.
All right, Mike, this week I wanted to talk to you about something you have heard of, a couple things you've heard of, but I want to do something a little different. I kind of want to try to tell a little bit of a story here.
Ooh, will there be hobbits?
So I want to tell you a story, Mike. The story begins in the summer of the year 2000 at a conference called the ACM Symposium on Principles of Distributed Computing. They refer to this conference by the acronym PODC, Principles of Distributed Computing, and they've been running it every summer since 1982. So in year 2000, PODC was held in Portland, Oregon from July 16th to July 19th. This year, actually, if you want to go with me, it's in Huatulco, Mexico. I think we should try to go.
Oh, when is it?
It's July every year, PODC.
Yeah, let's do it.
So actually, you've heard other references to this conference before. This is the conference where they give out the Edgar Dijkstra Prize in Distributed Computing.
Oh, wow.
Yeah. You've heard of it. In 2000, they gave Leslie Lamport the prize for the clocks paper. It's a huge conference. How much money do you think you get if you get the Dijkstra Prize?
$12 million.
They gave you $2,000. You're close, but a little bit high. They give you $2,000, and you have to share it with all your co-authors. So, Mike, if you're planning to win this prize, you're going to have to try to write a paper all on your own so you can keep all that prize money.
I'm unmotivated to submit my entry now.
Okay, so picture this. It's the year 2000, Portland, Oregon. All these distributed computing researchers have gathered to talk about their fields. You can actually go to the website for the conference, which was published in the year 2000 and last edited, it says at the bottom of the page, in July of 2000. And it's like this little time capsule. The website's like white background, black text. There's no pictures whatsoever. It's like classic internet. There's links, and it's obviously just plain old HTML rented from a server. You can actually go to the website. You could see how to get to the venue, which is the Portland Marriott City Center from the airport. And it feels like you're looking at this website. It feels like you travel back in time. Like you're right there about to go to this conference. You're feeling Internet 2000. They have this page talking about Portland itself, and the page starts with the header, blueberries, in all capital letters and 3 exclamation marks. It's just like, it's like friendly and gentle, and like they're like, yeah, come to Portland and pick blueberries.
Yeah, it's not a project or an acronym or a euphemism. It's talking about actual blueberries.
Yeah. I was like, what did they say to do in Portland in the year 2000? I clicked the link. I just started laughing. You can see this for yourself, friends. We'll put the link up there. Okay. On the first day of the conference, about 5 p.m., Leslie Lamport actually gave a whole tutorial on writing TLA+. TLA+, very, very new at the time. I looked up the weather, and it was 90 degrees that day. So people are coming into this how to write TLA Plus workshop. They're all sweaty from having picked blueberries all day, and they're ready to learn for the first time how to do TLA Plus.
Sweet.
You can picture this. We built we drew a picture in your mind.
Yeah, it sounds like a place I would have liked to have been.
It does, doesn't it? Doesn't it make you feel like, oh, I kind of wish I could have been there, fly on the wall? Okay, so that was Sunday. The conference started July 16th. But then on the Wednesday, the last day of the conference, in the morning, there was a talk. It was like they said, this is an invited talk. A guy named Eric Brewer. I have a feeling you've heard of him, Mike. He was faculty at UC Berkeley, and he gave a talk called Towards Robust Distributed Systems. And it was only about 60 degrees at 8:30 in the morning. On that Wednesday, it wasn't 90. So people come in, they see this invited talk, and here's the synopsis on their website. The synopsis reads, current distributed systems, even the ones that work, tend to be very fragile. They are hard to keep up, hard to manage, hard to grow, hard to evolve, and hard to program. In this talk, I look at several issues in an attempt to clean up the way we think about these systems. These issues include the fault model, high availability, graceful degradation, data consistency, evolution, composition, and autonomy. There's a lot of stuff thrown in there, right? Continuing on, the synopsis says, there's an important line here, these are not yet is in parentheses, these are not yet provable principles, but merely ways to think about the issues that simplify design and practice. They draw on experience at Berkeley and with giant scale systems built at Inktomi, including the system that handles 50% of all web searches. Mike, have you heard of Eric Brewer?
I have, yes.
Yeah. Can you tell us where have you heard about? How do you know him?
Well, I know him a little bit because of what he talked about here and the fact that it became sort of well-known subsequently. But he was also one of the founders of a company called Inktomi. I'm not exactly sure how you pronounce that, but we used to call it Inktomi back in the day.
Mm-hmm. You've heard of the company. I had never heard of it.
Yeah, well, it was pretty well known in the late 90s, early 2000s, and then not 100% sure about this, but I think it got acquired by Yahoo. And like many things that got acquired by Yahoo, it sort of got sucked into their vortex and was never heard of again. But I think they did use parts of what they had built at Inktomi. But
do you know what Inktomi did? It's a search engine.
Yeah, part of it was search. I also believe they were kind of one of the early players in what is now called content data networks or CDNs.
Yeah, I saw a talk with him. I listened to an interview with him, and that's what he said. It was an early CDN, early web searches.
Yeah, and I think they were acquired primarily for the CDN part, but I'm not sure about that. But I also suspect that's probably where he encountered a lot of these issues that he talks about.
The reason I wanted to talk about this, the reason I mentioned this synopsis is this talk in 2000, first public description of something that at the time was called the CAP conjecture. And very soon afterward, this idea became pretty well known. If you're listening to us talk about it now and you've heard of this, you've probably heard of it as the CAP Theorem. Now, that's part of the story I want to get to eventually. For now, we're just going to call it the CAP conjecture. And the reason it's a conjecture is in this sentence. These are not yet provable principles. Do you know the difference between conjecture and theorem? I actually had to look this up.
Well, yeah, informally, a conjecture is something which is proposed and sometimes assumed to be true or expected to be true, but not proven to be true.
Mm-hmm.
There's many of these in the math world. There's the famous Goldberg conjecture, I believe, has
Mm-hmm.
to do with prime numbers and things like that. But yeah, that's my distinction. Is they're usually things that are proposed but not proven.
And the theorems are things that have been mathematically proven.
Correct. Yeah.
So Brewer, he actually works at Google now. I listened to some interviews with him. I read some interviews with him. He's got a really interesting history, and he's kind of been like a Waldo figure in the background at various important moments in your work and my work, actually. So he joined faculty at UC Berkeley pretty young. He said he was 26 when he started working there. And he said in later interviews that he actually had grad students who were older than him when he joined. And he was there like right when the web was starting to become a huge, well-known thing. He was interested in clustering machines to solve these like massive internet scale problems that he intuited were about to happen. And he thought that search engines were probably the first problem that would come up that would need like really large scale compute. And so he wanted to do research to contribute to this moment in time for technology. And as you said, like in Toki, his company that he started, they were like an early CDN. They didn't really call it a CDN at the time, but they were building these massive databases to serve traffic. This was pre-cloud and even mostly pre-virtual machines. It was like they're running data centers with like raw machines and trying to figure out how can we build databases and serve traffic from those databases. CAP conjecture, really, he's talking about distributed systems. What do we think, Mike? Is that a thing? Is that a term people are going to know listening to us?
I suspect most will, but I know that we're going to be using some terminology here that's mostly has to do with distributed systems. And, so maybe we should give a little bit of background on what we mean by that, since, we're going to talk about what CAP stands for and what those things mean. And those are mostly applied to distributed systems.
Mm-hmm. All right. Why
So
don't you do that?
so like in the early days of my career, I started professionally in the late 80s, and that was kind of the early days of distributed systems. People were already doing research on it and stuff, but most people probably would not have encountered like a distributed database system at that point in time. We had things like X Windows, client server stuff like X Windows, and
Thin clients.
yeah, thin clients and terminals that you could run on your desktop that connected to server machines. And we occasionally built things that communicated across sockets and things like that. But what we're talking about here is, there was a point in history where if you were building a system and you started to run out of capacity, you just went out and got a bigger computer. And then at some point, somebody realized that you could achieve certain things by sort of spreading out that stuff across different other computers. So like one thing that we will talk about here is that if you have multiple computers and your system has access to both of them, then if one of them goes down, you still have one of them available to serve requests.
Yeah. Brewer gives the example of Gmail. He's like, there's no computer that exists that you could hold all the Gmail users on. You by nature of that problem,
Right.
you have to put data on different machines.
Right. So things like, making certain that your service is always there to serve requests is assisted by having things on multiple computers, and scale is assisted to a certain extent by having things on multiple computers, because now you can sort of spread out the requests across a bunch of different machines. So you gain some things by distributing the system across multiple computers. And what you get in exchange for that is extreme headaches. very, very, very complicated problems, which are still people are still trying to solve to this day. And so, I mean, I think the things that we're going to talk about in terms of what the CAP conjecture at this point in time is talking about are things that really apply to this sort of distributed system where the data and the request load is spread across multiple machines.
Yeah, that's a fair point. And it's probably easiest to think about it in terms of a database. If I wanted to put all my data in a database, but I have so much data that I can't hold it all on one machine, or it's not impractical to do so, I need to break it up somehow. And now it's distributed. So that's a
Right.
distributed database.
And you can think of the work that Brewer was doing at Ptolemy as being, like the CDN you can think of as being a sort of distributed database. What you're trying to accomplish there is you've got data or you've got web content that you want to put close to the client machine of the requester. But that means that you have to replicate it across geographic locations. And so it is, in a sense, sort of a very widely spread out distributed database.
Yeah, you might be listening to Mike and I right now via the magic of a CDN because the actual file that serves this show, it might be like a 500 meg file. And if everybody in the world who wants to listen to it, we had people from 32 different countries listening to our show last year. If that file is located on a server, let's say in England, I don't know, just for an example, then it means everybody in the world has to have their network traffic bounce around the internet, finally land on England in order to then extract 500 megs of audio file. Only 100 megs of it is even interesting or funny, though. Sorry, bad joke.
Most
Anyway,
of my part, yeah.
So the CDN content delivery network, what it can do is you can actually propagate that file closer to where people are going to ask for it, right? But you got to know where it is. So it's really like a kind of database problem. Common CDN now would be like Cloudflare, Akamai, if you've heard of Cloudflare. So it's a pretty interesting problem. And it really does, I think, boil down to kind of a distributed data problem. Mike, you said that you get a whole lot of problems when you start dealing with distributed systems, but I have a comment to that, a rejoinder. You might get problems, but you also get to rub elbows and pick blueberries with Leslie Lamport in Portland. So it's a fair trade-off.
Yeah, I would put up with a lot for blueberries.
With Lamport? Blueberries with Lamport?
Yeah, with or without Lamport, I am a big fan of blueberries. So
Yeah, me too. Yeah, I just had some this morning. Okay, so we keep talking about CAP, but we haven't actually defined it. So CAP is an acronym, CAP. And when Brewer talked about it in 2000, the C, A, and P that he introduced here are for the following, each letter maps to a word or phrase. So the C stands for consistency. The A stands for availability. And the P stands for partition tolerance. So what does that mean? Well, the C, the consistency part, says that every member of this system, again, it's a distributed system, so maybe we have a number of different machines that are all participating. If they are consistent, it means they all agree. Availability is if I have a number of different machines in the system, if I send a request into the system, I'd like to get some answer. I'd like to get it pretty soon. So availability means I generally am going to get an answer. I send in a request, the system's available, it sends me an answer. If the system's not available, I send in a request, I do not get an answer. And finally, partition tolerance, that's the one that always sounds a little weird. That pretty much means I have a bunch of machines in my system, and the network is the way in which they communicate with each other. But that network has the possibility of getting partitioned. And what that means is it's possible that some of my machines can't communicate with some of my other machines. Maybe I've got this lonely machine way out here and it's in a different data center. And for some reason, it can't get out on the network to talk to the other ones. And that is a network partition. So partition tolerance means that somehow the system continues to function even if one or more of these nodes is totally not reachable. Now, this is an acronym, CAP, C-A-P, consistency, availability, partition tolerance. And Mike, does it remind you, when you think of CAP, do you think of any other acronyms that are related? Are there others that you link it to, or not necessarily?
Well, I think people do tend to associate this and also confuse this with the ACID acronym that's used in
Oh.
databases.
Okay, so I have an embarrassing admission for you. I almost always forget the I and the D.
Yeah.
I kind of come up with them after time. ACID is an acronym related to databases. With the amount of experience I have telling you, admitting publicly on air that I can't always remember what the I and the D mean, probably not a good look for me. Uh, Tell me what ACID is, Mike.
So it's an acronym that is basically applied to qualities that you want from a database in terms of transactions on that database.
Okay, so what
Um,
are they? What do the ACID stand for again?
so the A is atomicity, the C is consistency, the I think, is isolation, and the D is durability.
Yeah. What does atomicity mean, you think?
Well, I think the basic idea is that so when you make a transaction on a database, there may be like multiple things you do in that transaction, and so you want to make sure that everything succeeds or nothing succeeds. So you don't want there to be like part of the data gets written and part of it does not, and then you give up. You want it to either succeed entirely or do nothing at all.
And isolation, interesting too. You can run multiple transactions that don't really relate to each other. You can run them at the same time because those transactions are isolated, right? Do I have that right?
Yeah, that's right. And like a lot of databases will even give you different sort of levels of this.
Mm-hmm.
So, like for instance, you may decide that it's okay to be able to read a database while a transaction is in process.
Mm.
Or you may decide that if you see a transaction in process on a particular table, you want to wait until that transaction is complete before you do the read. And so you wait for it. And so there's sort of different levels of this too.
But ACID is kind of like a set of guarantees or a set of properties that we generally want our databases to have, right? It's not like, oh, ACID, I can give you a little bit, but I probably won't give you all of it. It's like most databases promise ACID guarantees. Am I right? And maybe they have like
Yeah,
variations or sort of
yeah,
vagaries.
they do, and I think this is mostly associated with, in my head at least, it's mostly associated with relational databases,
Right, right, right.
SQL data,
PostgreSQL,
yeah,
MySQL. Yeah.
Oracle, things like that.
Oh, the name we do not speak of. So here's a weird thing about CAP. CAP, again, consistency, availability, partition tolerance. Unlike ACID, a set of properties or guarantees that we say, yes, I prefer to have a relational database that has these things. If it has durability, someone goes in my server room, they shut the light switch off, and accidentally I wired up my server to that plug, and boom, the database server turns off. When it turns on again, I hope there's some durability in my data. Hope it's still there. I want those ACID guarantees. Here's the weird thing about CAP. CAP says you can only have 2 out of 3. It's like that old joke. You can have it fast, cheap, or quality. Pick 2 out of 3.
Yeah, exactly.
Right? You can only have 2 out of the 3 of the CAP properties. So you can have consistency and availability, but not partition tolerance. Well, you might go, well, what does that mean? It's like you probably can only have consistency and availability if you run one machine. If you run multiple machines, you got partition tolerance, you could probably only have availability and partition tolerance, but you can't have consistency, availability, and partition tolerance. You have to pick 2 out of 3. It's surprising and weird that you can't have all of them. I think programmers, they don't like being told they can't have things.
Well, it is a surprising thing, which I guess is why it started out as a conjecture and took some smart people to prove that it was actually a thing.
Brewer says at the time he's trying to make this argument that he said, this is a quote from him, you have to make this choice. He said people would assume they could have everything they wanted, and they would say, like, oh, but I have snapshots in my distributed database. And he says, this is a quote from him, he says, snapshots by definition are not consistent. You have to actually pick. in an interview a couple of years ago, he mentioned that he first stated this well, he's teaching this course at Berkeley in 1998. He'd been working on CDNs, as we said, and he had built this database optimized for availability over consistency. And so he went to talk about it at this big database conference, and people were like, nah, that's not a database because he wasn't prioritizing consistency. So now I think CAP is like a pretty widely known thing. And we often play this game where we look at new database offerings or we look at their marketing materials and we're like, okay, where do you fall on the CAP axis? Are you CP or AP? And Brewer gave a keynote at PodC 4 years after this invited talk where he talks about, look, you either forfeit partitions and you've got consistency and availability, or you forfeit availability and you've got consistency and tolerance to network partitions, or you forfeit consistency and you've got, well, you're available, but you're tolerating network, but you're not going to be consistent. He gives examples. He says, if you forfeit consistency, that's kind of like a DNS thing. It's eventually consistent when you do a DNS search. If you forfeit availability, that's like a distributed database, how they normally work, right? They're going to try to make sure they're consistent. And while they're doing that, they're not going to respond to your requests. They're going to make sure that all the data is in place before you can talk to them again. Or you forfeit your network partitions, and that's like a single site database, a single server, right? It's not distributed anymore. It's not like robust in case the machine goes down or the network goes down, but the consistency and availability get a whole lot easier on that single machine. And if we could kind of dig in a little bit, if I send in a write request to a distributed database, I've got 3 machines maybe, that write request goes to A, and it needs to end up getting also to B and C. I've got partition tolerance. I've got multiple machines. If I want B and C to respond to questions before they get the update I sent in that went to A, well, I want it to be available, but I might get the wrong stale answer. If I don't want them to respond, I want to wait until the information propagates around the system. Then I'm looking for consistency. How'd I do? Does that make sense? Did I describe it?
Yeah, I think a couple of points on that. So, what's going to happen in a database like this is you're going to do a write. Say you've got like A, B, and C, like you said. Somebody's going to do a write to, let's say, A. That update to that piece of data has to somehow be communicated to B and C as well.
Mm-hmm.
If you write something to A and then you read that item from B, you want to get the same value back on B that you got from A. So that's sort of where the consistency part comes in. What could happen here is, since you've got 3 servers, if somehow the message that you need to send from A to B to C and C doesn't happen, then you are not partition tolerant, essentially, right?
Mm-hmm.
So, the B and C are still available. You'll get a response from them if you ask them for the data, but it won't be the same. It won't be consistent with what's on A.
Yeah.
The other point is that consistency here is slightly different than consistency in ACID.
Oh, you're getting ahead of me.
Yeah, we won't go into that in detail now, but it's just to note, it's a slightly different definition than what people use in the ACID, in consistency in the ACID definition.
That's fair. I kind of wanted to present, if you're listening to us and like, wow, you're really oversimplifying, I wanted to present kind of a simple version of this CAP at the beginning here. And there's a reason for that. I have kind of a thesis behind my story. Mike, here's my thesis for you. The CAP theorem, I think, it's the most widely known distributed systems result in our industry, right? Not among researchers, I'm saying working programmers. If you're a working programmer and you've heard of any single distributed systems topic, my bet, it's CAP theorem. What do you think? Do you buy that?
I would buy that. Yes. In fact, I find CAP theorem interesting in that it just, at some point in my career, kind of came out of nowhere, and then I just started seeing it everywhere.
Yeah, right. You heard people talk about it a lot, didn't you?
Yeah, and it seems almost like I don't know, like some sort of rite of passage. It's like, bro, do you even CAP? Yeah.
Fun facts about Eric Brewer. He eventually leaves the Cal faculty. He actually joined Google about 10 years after the PodC, 2000 PodC. When he goes to Google, he gets involved in infrastructure, deployment. He gets involved in how they're hosting their services. He gets involved in Borg. And he eventually works on developing and arguing to open source Kubernetes. I didn't know that. Did you know that? I had no idea.
I did not know that. No.
Yeah, he has like a lot of interesting descriptions of what they were doing. He's pretty fun to listen to. He said I listened to his interview with him, and he said, well, at Google they had this deployment platform called App Engine, and it's almost like kind of like a serverless early functions as a service thing. And he said it's like it was too abstract to solve the problems people wanted to solve. But virtual machines, on the other hand, are too specific. It's like you got to spawn the virtual machine and load it up with system dependencies, and then you can deploy your code on it. And he said Kubernetes, he actually used this phrase, is the Goldilocks sweet spot. It can run anything. It abstracts the machine, abstracts system dependencies. It allows the developers to just sort of shove their code into a place and have it running. And when he was asked, well, why did you want to open source it? He said, I felt it was too big a change in the industry not to get other people to participate. And he said, and I saw this interview with him in 2015. He was like, we're getting like 400 pull requests a day. I can't even keep up. And I was like, geez, buddy, it's going to be a lot crazier in another 10 years.
Yeah, that's funny.
Yeah. So I was like, wow, this guy, CAP Theorem, and he goes to work at Google, and he's like involved in open source and Kubernetes, and now he still works at Google doing infrastructure stuff. So, I mean, this guy has directly affected the work that I do because I do a lot of stuff deploying on a Kubernetes. So that's pretty interesting. So back to my thesis. My point was, if you've heard of a distributed systems topic, I'm betting it's a CAP theorem. And I think my question is, why? Why this particular idea? And I want to try to go a little deeper into the theory and the story to try to figure out if we can answer that why. Why is this idea the one that people so often bring up and hear about? So I want to take you back in time. We've now briefly talked about the CAP conjecture. I want to take you back in the story a couple decades earlier. So we're going from PODC 2000, where Eric Brewer first publicly mentions a CAP conjecture. And we're going to go back to 1985. It was a cool time. You had Back to the Future either that year or the year before.
Yeah, it's good era. I think I was still in college then.
1985, good year. So in that year, there was a publication of this paper that became hugely important in our field, in the field of distributed systems. It was a foundational and ground-shaking idea. It inspired loads of research in distributed systems theory. The paper is called The Impossibility of Distributed Consensus with One Faulty Process. Here's what the abstract says. The consensus problem involves an asynchronous system of processes, some of which may be unreliable. Okay, so first point, we got async system. They send messages to each other, but they don't get responses. It might be unreliable. Some of them might die. Continuing on, the problem, they write in the abstract, is for the reliable processes to agree on a binary value. Okay, so let me describe that. So they're just going to decide a 0 or a 1. Does that sound like a fantastic system or what?
Yeah, I wish all systems worked that way.
Do you? Oh, it sounds so boring. Hey, Mike, I'm going to build this distributed system, and the goal is for each node in the thing to decide 0 or 1. And we're not even going to decide it multiple times. We're going to figure out if you want a 0 or a 1 with your order, and we're going to stop.
Yeah, I just like the idea of like the user story and on the Jira board. You know, it's like write this system. It's going to be super complicated, but really, we just want to turn this light bulb on. So.
That's a good point. Turn the light bulb on or off. It is shown, they write, that for every protocol for this problem has the possibility of non-termination. It might run forever, even with one faulty process. By contrast, solutions are known for the synchronous case. So in this asynchronous case, you've got a group of nodes. They're trying to agree on a binary value as 0 or 1. If you have one faulty process, there's no solution that can definitively say they will definitely decide at some point and stop.
Yeah, which I think was both surprising and probably depressing to to some people.
That is hella surprising. That's what I'm going to say about that. That's hella surprising. So this paper is very well known. It's usually called FLP. It's so famous. It's called FLP. FLP is the last names, the first letters of the last names of the authors, Fisher, Lynch, and Patterson. The paper's so famous, they just call it FLP, and everybody knows what they're talking about in the field. It's kind of crazy to think that in this specific model of a distributed system, you have one process crash, then it's mathematically impossible for the system to achieve consensus. Remember how I was telling you about PODC, the conference in Portland, the Dijkstra Prize in 2000, Lamport won it? Remember that?
Yep.
In 2001, the next year that conference, this paper won that prize, this 1985 paper.
Yes, but were there blueberries?
I'm sure. I don't know where they held it in 2001. And Mike, I did not look up the weather before you asked me. Okay, so let me just give you a little bit more of a chunk from the paper to try to understand what they're talking about. In this paper, I love this line, by the way, Mike. This is from the introduction. In this paper, we show the surprising result that no completely asynchronous consensus protocol can tolerate even a single unannounced process death. We assume that the message system is reliable. It delivers all messages correctly and exactly once. Nevertheless, even with these assumptions, the stopping of a single process at an inopportune time can cause any distributed commit protocol to fail to reach agreement. So I guess we can define a couple things. What is consensus? Typically, consensus means three things in the literature, right? Now, this is more of a strict definition than you and I would use informally. Like, I want consensus on my program. Consensus here has three properties typically. One is termination. All of the processes have to complete at some point. So you know that the algorithm has finished. Two is agreement. This is probably the obvious one. They have to agree. All the correct processes, the non-faulty ones, the ones that successfully completed, they have to have the same value. So if there is any disagreement there, all bets are off. And there is this one that I kind of always forget about, but that's the validity argument. You could write a program which trivially says, we're supposed to decide 0 or 1. One time in math class, our math teacher said, what's the answer to this? And I said 4. And she said, are you just yelling out numbers? And I said, it's usually 4. And she said, this is not a valid contribution. This is what she's talking about, validity. You can't just arbitrarily be like, yeah, we're quote unquote deciding 0 or 1, but I just hard coded 0 as my answer, right? Like the value has to have been proposed by one, or even for stronger consensus, by all. Like all of them have to have successfully proposed. So that's the validity, right? The answer has to have been proposed by one of the machines. Now, they're working in the paper with a stripped down formal model. It's not like supposed to be an analogy for the internet, right? I mean, this is 1985. They're saying we're going to strip it down to these actors and we're going to call this a configuration of the system. And again, they're dealing with quote unquote async. Well, what's async?
In FLP, the messages that are sent to the machines are asynchronous, which here means that nobody really knows when they're going to show up or what order they'll be delivered in.
Yeah.
And it means you can't really rely on timeouts to decide that one of the processes is faulty. A correct implementation must end at some point with a correct value. The model that this FLP uses also assumes that the messaging system is reliable, so it really is expecting the messages to get delivered and only be delivered once. So when they say a faulty processor, what they mean is one that just doesn't process the messages anymore.
And the fact that there's no deterministic solution for achieving consensus if you have one failure is just like, it's so surprising. I was watching this talk Nancy Lynch gave a few years ago. She's the L in FLP, Nancy Lynch. And she said, what if you just waited? She said, hypothetically, what if you just wait for that one faulty process to wake back up and then tell it, hey, we decided this value. You died. You're awake now. Here's the answer. And she said, even that doesn't work. There's no deterministic solution. That sounds kind of nutty.
Yeah. I guess, so this is 1985, and I was not working professionally yet, but the other thing that's kind of surprising to me about this is that there was enough research going on in distributed systems theory to motivate this problem. It just, I don't think there were a lot of. I mean, there was really no public. There was the ARPANET then, but there was really no public internet. Facilities with lots of internal network were still pretty rare at that point in time. So, just the fact that there was enough stuff out there to motivate this research is kind of interesting.
Yeah. You start thinking about like network communication, and we don't really have guarantees about how fast messages are going to get delivered, right? I mean, it might take a really long time. Someone might actually step on my Ethernet cable, and those bits are going to be so slow getting to me.
Yeah, I think there's also sort of the implication that the messages, since they're going into this queue, there something could happen to the network, but then the network could recover, and then they could get, since it's asynchronous, they can then get delivered when the recovery happens. So if the squirrel does chew through your cable, once you replace the cable, the messages could get delivered.
I get a little lost. Okay, I get really lost understanding the proof in the paper, but people in the field say that the way they prove this is really creative and novel, and it's a technique that was then used elsewhere. The authors actually, here's how they describe what they're trying to do. This is their description later on when they got the Dijkstra Award. They say the intuition behind the impossibility proof's pretty simple. Initially, either decision 0 or 1 is possible. Remember, we're deciding a binary value. So we start out, we assume a correct algorithm. At some point in time, the system as a whole must commit to one value or other, either 0 or 1. That commitment must result from some action of a single process. Suppose that process fails. Then there's no other way for the other processes to know the commitment value. Thus, they sometimes make the wrong decision. So this is a contradiction. There is no correct algorithm. We assume a correct algorithm, and then we demonstrate the contradiction that there cannot be one. And they move on to say this simple argument that there's kind of intuitive feel for, it's actually pretty difficult to make precise. The subtlety of this is them describing it. The subtlety of the argument became apparent to us when we tried to explain the result to others. Many people expressed skepticism and disbelief. It took a lot of time and careful polishing of the proof on our part before the correctness of the result became generally accepted. I can kind of imagine that. Like, can you imagine trying to tell people, hey, I figured out that you could never achieve this asynchronous system of processes. You're just trying to decide 0 or 1 between those. One of them fails. All bets are off. You tell me that, I'm like, oh, come on. There's got to be a way to write a program that achieves that.
Yeah, they do go to quite significant lengths to make it formal. They establish this thing initially that shows that. So they talk about there being a series of steps from the initial configuration that results in another configuration, and they establish this thing initially that says that these sequences of steps sort of commute, which is sort of implicit in the way they've defined it, but they still establish that as a lemma. And then they also establish that there's at least one. There exist starting configurations where the problem is not already solved. So, I'm not sure that would have occurred to me, but the first thing they establish is that we can at least say that at the beginning there has to be some configuration that doesn't already solve the problem.
So the one of the weirdest parts is, and this is also surprising to me, they say later on, people talk about how solutions to this problem actually exist if you start introducing randomization. And this is where stuff like Raft comes in. Like Raft has a randomized leader election election timeout, right? And you pick a random value from half of the election timeout that you started with to the election timeout. So randomly select between half and the value. And that randomness is enough to actually determine that you're going to make progress in your system. So this paper, huge deal. Paxos, Raft, other results of distributed systems come out of this FLP result. They're inspired by it. They're responding to it. It's a hugely important part of the work of this field. When they won the Dijkstra Award for this paper, the citation, the description of it, the people who are writing, like, this is why we want to give it to them, they write, this result has had a monumental impact in distributed computing, both theory and practice. System designers were motivated to clarify their claims concerning under what systems the circumstances work. And I kind of like that line because it's like, hey, you can't just make up a bunch of bullshit about stuff you claim to have done, because now there's this result which says, wait a minute, you are claiming that this system achieves a thing that we know is mathematically impossible.
You can't just say it works on my machine.
It works on my machine. It works on my half a dozen machines, Mike. And someone else writes, this result has been extremely influential, both because of its implications and because of the proof technique it pioneered. Its importance stems from the fact that consensus lies at the heart of many practical problems, including atomic commit, leader election, atomic broadcast, and the maintenance of consistent replicated data. One thing that's funny about FLP is it's an impossibility result. I like this term, impossibility. It proves that some particular set of properties is impossible to achieve under these specific conditions. That's what CAP conjecture was about. You got to pick 2 out of 3. 3 out of 3, impossible. So under these conditions, you could see how like building a system with a particular set of goals could actually be impossible in practice. And I almost think there's something like in the personalities of programmers where you tell us stuff's impossible and we're like, probably for you, but I could probably pull it off, right? You know what I mean? Isn't that like a common kind of response? If people aren't aware of what's actually practically impossible, then they might still be trying to build these systems that promise impossible things. So we can use this to know like when somebody's making outlandish claims about some system.
There's also, I think Lynch sort of implies this too, but the interesting things about impossibility results is that impossibility does not necessarily imply impractical.
Yeah. That's definitely true. I mean, people have built a lot of cool stuff. Go ahead, though.
Yeah, so like, people do build databases that work despite this result and the CAP result, but also, things like, if you've studied computational complexity, you know about NP completeness and P versus NP and that kind of stuff. But in the meantime, people do build SAT solvers that, run in finite amounts of time. So people have figured out ways, even though they suspect there's no polynomial algorithm for the perfect solution for these things, they found practical ways or, ways that are going to be correct within some probabilistic limit.
Right.
For a system like this, people have thought for a long time that consensus could probably still be established if you had enough processors that were not faulty. But the FLP result proves, in fact, that even if there's only one faulty process, there's no reliable series of steps that will guarantee consensus. So really what FLP says is you can't guarantee an outcome in all scenarios. It's always possible to hit a sequence of events which invalidate your attempts at consensus. So in other words, we can't really build an algorithm that is guaranteed to terminate with a correct result. A deterministic solution that would always work in the face of failures of some processor is what's demonstrated to be impossible by this result.
Well, I mean, what you just said is pretty heady, but that's one of the cool things that happens in our field. We have research results which point to something like a theoretical ceiling for what's possible. And those get people real excited and interested in still achieving something. You're telling me there's a limit. And now my question is, how close to that limit can I get? Like how much can I still achieve? Actually, I do want to talk a little bit more about Nancy Lynch. Nancy Lynch, again, she's the L in FLP. She was born in 1948. She's been a professor at MIT since 1982. She also taught at Tufts and USC. She's won a huge number of awards. She actually wrote the standard textbook on distributed systems called Distributed Algorithms. This is someone who has a lot of influence in the field, has contributed huge numbers of results and been recognized for it. She has this paper in 1989. It's got a flippin' title. It's very long, but it's like 30 pages long. It's called 100 Impossibility Proofs for Distributed Computing. It's kind of like, you like that impossibility proof. I'll give you 100 more, my friend.
One of my sons reminded me of this bit they did on the show Parks and Recreation, where the local like public radio station is. They're doing this thing about how I heard people like jazz, so we're doing this thing called Jazz Plus Jazz, where they play 2 jazz albums at the same time.
Jazz plus jazz. So Nancy Lynch, in this paper, Hunter, a Possibility Proofs for Distributed Computing, she writes this paragraph I really like. What good are impossibility results anyway? They don't seem very useful at first, since they don't allow computers to do anything they couldn't previously. Most obviously, impossibility results tell you when you should stop trying to devise or improve an algorithm. This information can be useful both for theoretical research and for systems development work. I love that paragraph. She's like, you know what? I've got this impossibility result here, and what it tells you is to stop working. Just stop, okay? Kick back, go do something else for a while. This to me is a fascinating part of the appeal for this work. What good is it for programmers to be told, what you're trying to do right here, my friend, is impossible? And not only that, it's mathematically impossible. It's not just someone's opinion about how it's going to be really hard or it's going to take a long time. It's like the speed of light or something.
Yeah, it's not just intractable or computationally complex. It's literally can't be done. So.
Yeah, there's something kind of cool about being shown the wall and saying, yeah, you're never going to get over that one. All right, so we have talked about the introduction of the CAP conjecture at PodC 2000. We've now gone back to 1985. We talked about FLP, and we talked about Nancy Lynch and impossibility results a little bit. Mike, this is only half of our story. I want to continue it next week in the next episode, Picture Me Coding. I want to continue talking about this story if you're up for it.
I'm curious to find out why CAP became such a viral, buzzy thing and FLP did not. So
stay tuned next week where we will answer that question for you, listeners.
The suspense is killing me.
So once again, if you'd like to reach us, you can email us at podcast@picturemecoding.com. We have a Patreon now. Patreon is Picture Me Coding. And if you'd like to sponsor the show, we will use your sponsorship to pay for hosting and professional editing services. This has been Picture Me Coding with Eric Aker and Mike Mull. Join us next week as we continue the CAP Theorem story.
See you next time.
Bye-bye.